Hey guys, so this is going to be the review for the pre-mock for your April 16th exam. We're going to be starting with the multiple choice. So multiple choice 1 says, rank the following compounds according to increasing pKa of the indicated hydrogens in the following compounds. So a big rule with pKa is you want to remember that low pKa equals more acidic. So in this case, they want us to rank the following with the lowest pKa's first and the highest last. So they want you to put your most acidic in the beginning and your least acidic at the end. Okay, now that we know exactly what they're looking for, we can start the question. So when we look at 1, 2, 3, 4, and 5, we see that actually right off the bat that 3 is one of the 7 strong acids that we learned in Gen Chem. So like HBr, HF, HCl, HI, all of those are extremely, extremely strong acids with pKa's in the negative. HBr, although you don't have to remember this, I'm just going to give it to you guys in case. HBr actually has a pKa of -9. So we can go into the answer choices and eliminate anything that doesn't have 3 as the first option. So only B and C have 3 as your first option. So you can go and eliminate D, E, and A. I always like to find the most acidic or like the most of whatever they're asking for and then the least. So now I want to look for the least acidic in this situation. So we have an alcohol and a carboxylic acid. Those are both relatively acidic. For your knowledge, a carboxylic acid has a pKa of around 5 and an alcohol has a pKa of around 16. So now we're comparing an amine and a carbon chain. Carbon chains never, ever, ever want to get rid of their H's. As we've seen, carbocations are very susceptible to attack because it's very unfavorable to have a carbocation. So just so you guys know, amines also have a pKa of around 30 to 35. Carbon chains have such a high pKa, I'm pretty sure it's like around 40, it could be 40. I'm not exactly sure, but in general, you don't really have to memorize pKa's if you know the behaviors. So you're going to look in your answer choices, and since carbons never ever want to be charged, you're going to find the one where 5 is at the end because it's the least likely to donate that proton or that H. And the only answer with that is actually C. So you don't even really have to go through the other ones because you already can eliminate B, leaving C as your only answer. But if you want to, obviously carboxylic acid literally has the word acid in the name, so you know that's going to probably be very low there, and you could see it's number 2. 4, alcohol is close next. It has 16 as a pKa. That's number 3. And then, like I said, amines are actually basic, so it's going to be your 4th choice. And that leaves C as the answer to number 1. So moving on to the next multiple choice question. This question asks us to rank the compounds shown according to increasing or more exothermic heats of hydrogenation. So, when you're thinking of heats of hydrogenation, the more stable your compound is, the lower your heat of hydrogenation, okay? So, more stable compounds have, I'm going to write an equal sign, equals lower heat of hydrogenation. I can't spell. Okay. So with that in mind, they're asking us to do it in an increasing manner. So they want the highest heats of hydrogenation at the end and the lowest heats of hydrogenation at the beginning. So what that means is if your highest HOH is at the end, these are also going to be your least stable, and your lowest HOH at the start, so these are going to be your most stable, and the trend is going to go that way. Okay, so with that in mind, we could actually tackle the question itself. So when you're thinking about comparing the stability of double bonds, the first thing you want to think about is how highly substituted the double bond is. So what that means is how many carbons or halides or anything other than H's is coming off of the double bond. So more substituted, it's the same thing as saying a more substituted carbocation would be a tertiary one, and a less substituted would be like a primary, even though that's very uncommon and wouldn't really happen. So more substituted double bonds are more stable. Whenever they ask you stability questions, it's actually usually easier to find the one that is least stable first and work back from there. So in this case, we're going to want to try and find our least stable one. With that in mind, it's important, with what I just said in mind, saying that more substituted double bonds are more stable, we're going to try to look for the one that's the least substituted. And in number 1, you actually have a terminal double bond. So terminal double bonds are the least substituted and the least stable. Least substituted, I'm just going to abbreviate that as subs, and least stable. Okay, so number 1 is going to be our least stable. So we can look in our answer choices and eliminate anything where number 1 is not the last option. So we see that A, it's the last one, C, it's the last one, and that's it. So we actually eliminate B, D, and E right off the bat. Okay. So I'm going to erase now. So now what I like to do is look for my most substituted and see if that helps. Our most substituted is going to be, our most stable, and see if that helps. Our most stable is also going to be our most substituted, and when comparing it, 2 is going to be our most substituted because we have 2 methyls come off of one end and 1 methyl and a carbon chain coming off of this end. When you look at 3, this one has 1 carbon chain and an H, so that's already less substituted. 4, same thing, you have an H coming off here, so that's less substituted. 5, you have 2 H's coming off, so that's less substituted as well. So 2 is going to be our first number, and we can see that both A and C actually have 2 as first, so we can't do any eliminating yet. So let's just keep going. Our next most substituted, although our answer choices both have 4 as next, we should double check. So 4 only has 1 H coming off of it, while 3 and 5 both have 2. So that does make sense that 4 is our next most substituted. So now we have to So now we have to compare between 3 and 5. So let's do that. When you're so the difference between 3 and 5, the only difference here is that 3 is in the E formation and that 5 is in the Z formation, or 3 is trans and 5 is cis. So when you're thinking about stability of double bonds, trans double bonds, or E double bonds are more stable than cis double bonds, or Z double bonds. So that eliminates 5 as being more stable, and then 3, since it's trans or E, is going to be more stable than 5. So we have to look in our answer choice for where 3 comes first, and that is going to be C. So you can eliminate A, and C is the right answer. Okay, so moving on to the next multiple choice. It says, which of the following pairs show valid contributors to the same resonance hybrid? So the best way to do these kinds of questions is to go in order and compare the second and first structure and see if any of them violate any of the rules of resonance, or if the structures are valid, and make sure that the overall charge is still the same, etc., etc. So this is actually a question from, or similar to what you would have done for exam 1, but you never know, he could retest you. So let's start with the first one. So they moved the electrons from the double bond up to the O, and this is actually a valid thing that you can do in resonance because you're not changing the connectivity or the number of atoms, you're not changing the overall charge because you have 1 plus on the C and 1 minus on the O, and this is actually the answer to this question because this one is valid. But we're still going to go through and look at why the other ones are not correct. So when you're looking at option B and you're comparing the two, they actually changed the connectivity of the atoms in this molecule because they changed CH2 to CH3 And you can't move the H from up here over down here. That's breaking the rules of resonance. Resonance, the only things that can move are the electrons, and that's it. You can't change the connectivity of the atoms. So B is out because they changed connectivity. So let's look at C. All right, comparing the first and second structure, they moved the double bond up to the O, which is okay to do, but the issue with this one is that they got rid of the negative charge on this O when they moved it over, right? So the net charge is not the same in this one and this one. So overall charge difference. They took the negative charge off the O to try and trick you guys, but you know that this O would still be negative. So C is out. Looking at D, this one is very, very obvious what is wrong with it. Carbon can only have 4 bonds. It cannot have 5. That's an expanded octet. So this is impossible, and that eliminates D. And looking at E, this one is actually pretty ridiculous. They just added electrons out of nowhere. Like, they didn't show where it came from. So that makes it pretty easy to eliminate this. Okay, so multiple choice 4 asks us which intermediate is formed in the rate determining step of bromohydrogen formation from 1-butene. So the first thing we have to do to answer this question is recognize which reaction bromohydrogen formation refers to. So the overall reaction of bromohydrogen formation is this. Using 1-butene as our reagent, it's kind of sloppy. The product is going to be a Br on the less substituted side being trans to an OH. Now, I'm going to give you guys the mech because you're going to need the mech to answer this question. Give me 1 second. Like most reactions in orgo, the first step of bromohydrogen formation is going to be the rate determining step. So, first step of bromohydrogen formation is rate determining. Sometimes you will see rate determining step abbreviated as RDS. So I'm just going to write that in here for you guys. I'm going to give it actually you could pause. So pause, write that down, and then I'm going to erase and include the mech. So you're going to start off with 1-butene. This is why naming is important, because sometimes, especially with a multiple choice exam, they're most likely going to refer to compounds by their name. So make sure you don't forget any of your naming rules. So you have 1-butene and Br2 with all of the lone pairs in place. The double bond, or the electrons in the double bond from 1-butene are going to attack the Br, or one of the Brs from Br2, and the electrons from the bond are going to move back into the other Br. So your product is going to be the ring formed by the attacking of Br, because what really happens is O'Connor doesn't show this in his alkenes notes, but while the double bond is attacking the first Br, the Br is actually also attacking the double bond back. So you get this ring intermediate being formed. Okay, so this is your ringed intermediate, and it's going to have a plus charge on it because it is bonded twice. It has 2 bonds on it, so that leaves it with a positive charge. And then you're going to have the Br anion. Okay, moving on to the second step. Technically, now that you have this intermediate and you know that the first step is the rate determining step, you can actually answer this question. But I'm going to give you the entire mech in case some people are confused. But this is in his alkenes notes, so I'm going to assume you have to know it. Okay. So now that you have your Br ring, the water is actually going to come in and attack the more substituted side. And this is how this is always going to be in this reaction. Okay? So that is going to cause the ring to open up. I'll draw the arrow in even though O'Connor doesn't. The electrons from this bond are going to go into the Br. So when the ring opens up, it's going to look like this. And of course, H2O is going to have a positive charge on the O. So now our next step is deprotonating the O. If you hear my dog snoring in the background, I apologize. Okay. So you're going to either use the Br anion or another round of H2O to deprotonate it. It doesn't matter which. In this case, I'm going to use the Br anion because I like everything to be neutral by the end of the reaction. So the Br anion is going to come, pull this H off. The electrons are going to return to the OH, and you're going to get your neutral product now. All right, so now let's go back and answer the question. Which intermediate is formed in the rate determining step? So step 1 is your rate determining step. This is your intermediate right here, this ring structure. So the answer to 4 is going to be C, because this represents the ring structure here when they write out the C's. It's not the line angle structure. Okay, moving on to multiple choice 5. For the reaction coordinate diagram below, which of the following is true? So just a couple important things to point out about reaction coordinates before starting this one. Okay, I'm going to make it bigger. So the peaks are representative of the transition states. So this is your peak. This is a peak. The valley is representative of your intermediates. And your reaction can either be exothermic or endothermic, which is the same as exergonic or endergonic. I'm actually going to choose a different color because that one's pretty similar to what I used. So exergonic means that you start at a higher energy level than when you finish. Endergonic means you go from lower to higher energy of the overall reaction, right? So in this case, we're starting here and we are finishing here. So this difference is a drop in energy, which means that our reaction is going from high energy to low energy, which means it is exergonic. So let's look at the answer choices. B is an intermediate and the reaction is exergonic. Okay, well, it is true that the reaction is exergonic, but B is actually a transition state. So A is going to be crossed out. Let's look at B. B is a transition state and the reaction is exergonic. Okay, so that follows through with everything that we have so far, but let's go and look through the rest of the answer choices. C. C is an intermediate and the reaction is endergonic. C is an intermediate because it's one of the valleys, but the reaction is not endergonic because you're not going from low to high energy. So you can eliminate C. D. C is a transition state and the reaction is endergonic. C is not a transition state because it's a valley and the reaction, as we've already established, is exergonic, so you can eliminate D. And your right answer is going to be B for number 5. So for multiple choice 6, they ask you how many transition states and intermediates will be found in the reaction coordinate diagram for the reaction shown below. So the first thing you have to do with these types of questions is you actually have to go and draw in the reaction and all of the steps. So on a separate sheet of paper, you should attempt it if you haven't already. So I will give you the mechanism for this reaction. So you start off with this molecule and the double bond, and the first step is going to involve the acid, and the electrons from the double bond are going to come and pull off a proton. Nothing new. And that's going to protonate the that is going to protonate the less substituted side, leaving your carbocation on the more substituted side. So your H will be here, and your carbocation will be here. And I'm sure now you guys recognize that there is going to be a shift of some sort. In this case, it's actually going to be a ring expansion. So in the next step, you're going to draw your ring expansion. Okie dokie. All right. So now we're going to go and number our carbons so we could find where the carbocation is going to be now. So 1, 2, 3. This is going to be the point. So this is 4 and this is 5. So 3 is now forming a bond with 4. But because 3 was originally bonded to 5 and 5 now lost these electrons, 5 is going to be where the carbocation moves to. Okay? So 1, 2, 3, 4, 5. Alrighty. So now we'll draw the methyl on and the point carbon at the end because we lost one of the carbons. So now it's not a ethyl, it's just a methyl coming off of it. And the next step of the reaction is going to be the water coming in and attacking the carbocation. Okay. Oops. How do I fix that? Okay. And your O is going to be protonated as normal. And for the last step, you're going to deprotonate water. And to do that, you're going to use, you guessed it, water. This little thing right here, I didn't mean to put that. Let me try and erase it. This isn't another carbon or anything. It's just a mistake. You can hear my dog drinking in the back. I'm sorry. Okay, I'll try to fix this one a little bit better too. Alrighty. So, water is going to pull off one of the protons. Let me do that in red. And that is going to give you your final product. Okay. So now going back to the question, it asks how many transition states and intermediates. So the transition state is going to correspond to how many steps there are in your reaction. So transition state, or number of transition states, equals number of steps. And the intermediates are actually the same thing as how many intermediates you have in your reaction. So let's start with the transition states. In this case, we have 1 step, 2 step, 3 steps, 4 steps. So we're going to have 4 transition states. So that actually gives you your answer right away. Your answer is B, because it's the only one with 4. But let's just count the intermediates. So the intermediates are going to be not the product and not the start, but these, right? So you have 1, 2, 3 intermediates in this case, because they're intermediates in your reaction. They're not the reagents, but I don't know why this did that. They're not the reagents, but they're also not the product. It's the intermediates of your reaction. So your answer for number 6 is going to be B. 4 transition states and 3 intermediates. Okay, multiple choice 7. Which of the following reactions produces a meso compound? So with these kinds of reactions, you actually have to draw out the products for all of these unless you're really good with it and you don't have to and you just know the product by looking at it, which I personally recommend you get to a state where you can look at it and draw it out without doing the entire mech before this exam comes, because otherwise you'll be wasting way too much time. But for the purposes of this video, I will go into detail with all of them. Okay, starting. So we only have 2 different types of reactions, which is H2PT And H2PT and H2PD are equivalent. They're the same reaction, just so you guys know. PT and PD are two different kinds of metals that behave exactly the same way. And then you have Br2 over CCl4. So H2PT, they didn't give you a mechanism to learn for, so I'm not going to give you the mechanism, but I'm going to let you know that the H2PT adds syn. So what that means is that the two H's, because H2PT is going to add two H's across the double bond, so the two H's will have the same stereochem as each other. So yeah, let me really quickly show you the overall reaction for H2PT. So say you have a double bond, you use H2PT, all you're going to get is a single bond because you're adding two H's here. They either are going to be both dashes or both wedges, but the way that I've seen it most commonly done, H2PT, the H's almost always add both dashes. So I would just keep that in mind when you do these. Make sure you make your H's add on both dashes. That's not like an established rule. It just seems to be a common theme in all the mechanisms that I've seen, even though he didn't ask you to learn the mechanism for it. Okay. So now we have to compare the Br2 CCl4 mech. So let me erase and I will give you the notes for that. Okay. So Br2 CCl4, in contrast to the H2PT, your two BRs are going to add anti to each other. And what this means, anti, is just that they will not have the same stereochem. So one BR is on a dash and one is on a wedge. And this is because of the ring intermediate you have in the Br2 CCl4 mechanism. So I'm going to give you the mechanism right now. Okie dokie. So I'm going to use one of the reactions actually in the product just to save us some time. I'm going to go with B to use as the sample mechanism. So you have a double bond, you have two methyls. Obviously the methyls do not have stereochem when you have a double bond. Be careful not to draw them on a wedge. Okay, so first the electrons from your double bond are going to attack one of the BRs. These electrons are going to return to the other BR. And let me draw in the lone pairs. I'm not going to do this all the time because it takes way too much time. But just because this is probably, for some of you, the first time you're seeing this mech. Although it shouldn't be. Okay, so I'm going to draw the BR ring in dashes and the methyls pushed out on wedges. It doesn't matter if you draw the methyls on dashes and the BR on a wedge. It makes no difference at all. I'm just doing it for the sake of this. And then for your next step, I didn't feel like redrawing that. For your next step, the Br anion that you created in the top step, which I forgot to write, is going to attack either side, in this case because they're both equivalent. So I'm just going to make it attack the closer side. And this is going to cause your ring to open. And when the BR attacks it, it's going to attack on a wedge and push the CH3 down to a dash. That way, the two BRs will be anti to each other because the original one is going to still keep being on a dash, and the new one is going to attack adding on a wedge. Okay? It's a little complicated, but it's okay. So here's the first one on the wedge, and the second one, oops, and the second one on a dash. And you're gonna have this product plus the opposite with like this BR being flipped. So you could either have this BR on a dash and this BR on a wedge, or this BR on a wedge and this BR on a dash. It's the same thing. It just depends on what you put the ring as in the beginning. If you put the ring on a dash or a wedge. It doesn't matter though which one you choose. Okay. So now they're asking which one is going to produce a meso compound. So let's see if this is R and S, basically. So on the left side, or on this chiral center, the BR is going to be priority. Then you're going to move this way, and then you're going to move this way. So it's S, but because your BR is on the dash, you're going to switch it to R. So the first one is R, and the second one, your BR is priority. It's on a wedge, so we don't have to switch it later. The rest of your chain on this side is going to be 2, and then 3 is going to be up here. Hold up. So it's going to go this way, and it's going to be R. So both stereo centers are R, and that means this product is not meso. So you can go ahead and cross out B. It's not meso. Okay, I'm going to erase, and we'll move on to the next one. Okay, so A. A is giving you, let me redraw it down here. Okay, so you're going to add 2 hydrogens across the double bond. In this case, like I said, I'm going to continuously put them on dashes when I'm using H2PT, just for consistency. So CH3 is on a wedge, H on a dash, H on a dash, CH3 on a wedge. Now this compound is not going to be meso because if you do the R&S designations, it doesn't work out for this one if you did it across this way. So let's move along. Okay, so for option C, one second. We're going to do the same thing. You have a double bond here. You're going to add your H's. You're just going to get this now. This compound is technically not meso at all, or not even, what would I say this? Not even considered for a meso at all, because this is no longer chiral, right? These stereo centers are not chiral anymore because both sides of the chain are equivalent. And you can only have a chiral center when you're bonded to 4 unique things. So that means C is out of the picture. Oh, also A from before. Okay, let's move along to D. So you have a double bond, you have 2 methyls coming off of it. And you're going to do H2PT. So I'm going to put the H's on dashes. All they're going to do is add across the double bond. So the CH3 is going to be on a wedge. The H is going to be on a dash. CH3 on a wedge. H on a dash. And let's do the stereochemistry for this one. So on the left side, okay, actually pause the video and try to do it first, just in case you haven't. Okay, I'm going to assume you have. So on the left side, this is going to be number 1, this is 2, and this is 3. So this is going to be S. On the right side, this is going to be, let me do it in a different color. This is going to be 1, this is going to be 2, this is going to be 3. So this is R. And this is your meso compound because it has the plane of symmetry, the S and R designation, and it's a ring. So D is the answer for number 7. If you want to try out E, you can go ahead, but you'll get that one is also not meso. I'm just getting tired of doing all of these now. It's also very repetitive of B, So basically you're just going to have the BRs being anti to each other in this case. It doesn't matter which side. And because you have 4 stereocenters, you pretty much know it's not going to be one of the products that they're going to make you check if it's meso or not, because they only do that with 2. So you're good. Okay, so multiple choice 8 asks, which of the following is the product of the reaction shown? So when you're actually taking this exam on your real day, you should be able to see the product in your head without drawing it out. But obviously, because I'm teaching it, I'm going to draw out the mechanism for this. Okay. So Br2 over H2O, you're going to have the ringed Br intermediate, and then H2O is going to attack the more substituted side, as we've seen before. So we're going to start with our Br2, and the electrons from the double bond are going to attack the Br. The Br is going to attack back, forming the ring, even though O'Connor doesn't show this. It's up to you if you want to show this step for yourself or not. They're not going to mark you wrong. I personally like to do it because it makes the ring more easily visible to me. And don't forget your lone pairs, obviously. So I'm going to draw this. In this case, I'm going to put BR on a dash. Oopsie. In the ring. It doesn't matter if you put it on a wedge or a dash, because you're going to get the mixture of products either way. And you're going to have the Br anion. Okay, so for the next step, it's going to be water coming in and attacking the more substituted side. Like so. And when water attacks the more substituted side, it's going to change whatever stereochem CH3 had. It's going to flip it to the other one when it pushes the Br over. So these electrons are going to enter the Br. And like I said, just make sure you remember that when H2O adds, it switches whatever stereochem the CH3 was originally on. So now, since it was originally on a wedge, it's going to be on a dash. And your H2O is going to be on a wedge. And your Br is going to be on a dash here. And then the very last step, as we've seen before, is just deprotonating. So you could either use water or Br, but I'm just going to write minus H, because you guys know that step already. And now you're left with OH, CH3, Br, plus the opposite of it. So OH on a dash, CH3 on a wedge, oopsie, and Br on a wedge. So just make sure you guys know, because this BrH2O uses anti-addition, the OH and the Br are never going to be on the same stereochem. So Br and OH are never going to be on the same stereochem for this reaction. And that's called anti-addition. Anti-addition. Okay. Let's look at the answer choices now and see if we can match this up with anything. So like I said, if you remember that little hint that I gave you, that Br2 over H2O uses anti-addition, so that the Br and the OH are never going to be on the same one, you can eliminate A right off the bat because it puts Br and OH both on dashes. You can eliminate any other ones. You can eliminate E because that doesn't even add an OH. That one adds 2 Br, and that's only the case if you're doing Br2 over CCl4, right? So Br2 over H2O, you're going to add 1 Br and 1 OH. Br2 over CCl2 is going to be 2 Brs. All right, let me write it down. Br2 over H2O equals 1 Br added, 1 OH. Br2 over CCl4 equals 2 Brs added. I'm running out of space. 2 Brs added. Okay. Sorry for how sloppy that is. Okay. let's go back to the reaction and see if there's any other ones we can cross out. Okay, so it doesn't seem like there are any others instinctively that we can cross out. So let's look at our product and see if we have any. Okay, so on this one, we have OH on a wedge, CH3 and BR on a dash. Let's see if that's the case in any of these. It is not. Okay, so let's look at the other one. The next one is OH on a dash with CH3 and BR on wedges. OH on a dash with CH3 and BR on wedges. Yeah, so we do actually have that one here. Do we see that? How those are the same? This and this. And that means your answer for number 8 is going to be D. So number 9 is actually from the alkynes chapter, so I'm not exactly sure if he's going to get to that before your exam or not, and this is the only question pertaining to that chapter on this exam, so let me know in the group chat when you guys watch this if alkynes is going to be on your exam. Even if it's not, I'm still going to go through this just in case. So the best thing to do is to just go through these reactions one by one. So you have your alkyne, and then you treat it with NaNH2, which deprotonates it and makes your alkynyl anion. And as you guys know, this is a really, really good attacking group. So let's just keep it going. And then as for step 2, they say CH3, CH2, Br. So basically you're going to combine your alkynyl anion with CH3, CH2, Br. And what it's going to do is it's going to attack the carbon that the Br is bonded to and kick the Br off. Like that. And it's going to leave this product. All right, so the next step is NaNH3. And what that does is that creates a cis double bond from a triple bond. So, did I add an extra carbon? I may have. Yeah, I did. Oopsie. Okay. So NaNH3 makes the cis double bond. So it's going to look like that. And the last step is going to be adding Br2 over CHCl2. And like I said before, this gives you the anti-Br2 addition. So you're adding 2 BRs trans to each other. So you're going to get a trans product. Let me count carbons because it's supposed to be 6. 1, 2, 3, 4, 5, 6. Perfect. With 1 Br up and 1 Br down. And that is your product for this series of reactions. So looking at what we have, okay, A right off the bat is the exact same thing as what we got. B is not right because that is adding syn, and in this case they're adding anti, so they'd be on opposite sides of the chain. C is adding an NH2, which is completely wrong. E would be adding on the same carbon, and that's not right because you're doing a ring, so you wouldn't get them on the same carbon. And finally, D is incorrect because they forgot to take away the double bond. So your answer to number 9 is going to be A. Number 10 asks you, which of the following solvents best promote an SN2 reaction? And SN2 reactions favor polar aprotic solvents. So I already wrote out a list of a couple polar aprotic solvents that come to mind that you should definitely know the structures of. If he mentions any other ones, then you should also know those too. Most importantly would be DMSO, acetone, and DMF. Those are definitely going to be the main polar aprotic solvents. So now we can go through the answer choices and see if any of these are polar aprotic solvents. So number 1 is actually the structure of DMSO. So we know that's going to be one of the answers. So you can eliminate any of the answer choices that don't have number 1 in it. So that's C and D. Number 2 would actually not be polar aprotic. Polar aprotic is a type of solvent that won't donate protons, right? So since an alcohol is relatively acidic, it would donate protons. So number 2 is definitely not going to be polar aprotic. Number 3, they're trying to trick you with a molecule that looks similar to acetone, But you have to remember that acetone does have the ketone on the top, not a CH2. So number 3 is not it. So you can eliminate B and E, and your answer is A. So let's look at number 5 just to make sure that makes sense. 5 is the structure of DMF, so that does make sense. And 6, they were trying to make it look like DMF, but it's not. And 4 is not even polar at all. So that leaves you with A as your answer to number 10. So number 11 asks, what would be the major product from an E2 reaction of the compound shown? So just so you guys know, whenever you do an elimination reaction on rings, specifically E2 reactions on rings, the Br has to be axial, and the anti-hydrogen also has to be axial. So what this basically means is that the hydrogen of choice has to be 1 carbon apart and axial, while the Br is also axial. So that would make it antiperiplanar in rings. So I'm going to write that down. E2 on rings. Br has to be axial. And the anti-H also has to be axial and 1 carbon away, because that's how you can form the double bond. They can only be 1 carbon apart. Alrighty. That being said, we can look at this compound that they gave us. In this compound, they gave us Br on equatorial. So we're going to have to do a ring flip, which we all remember, hopefully, from exam 1. Oops. Or chair flip, my bad. Same thing, though. Okay, so you draw your original chair, and you flip it. So you get Br on axial. Okay, 1 second. I'm going to draw this differently because it's taking up too much space. Okay, so in this case, the anti-hydrogens could either be here or here. Now, whenever we're doing double bond formation, it's very tempting to just go ahead and form the double bond in the more substituted way, or substituted way. So in that case, that would be this. But the reason we can't do that is because that H is actually equatorial when our Br is axial, so we can't eliminate it. And because CH3 is axial, there's nothing we can do. So we can't form the double bond that way. The H that we're going to have to remove is going to be this H. And your double bond is going to be able to form this way. So now, converting that back into a ring. Excuse me. All of your methyls, see how they're all down? That means they're going to be cis to each other. So they're going to either be all on wedges or all on dashes in your final product. It doesn't matter which, as long as they're all cis to each other. So since they're down, I'm just going to go ahead and arbitrarily draw them on dashes. But know that if they're on wedges, that is exactly the same thing. And since the elimination product formed on the less substituted side, the double bond is going to go here. Not here like we would have wanted to put because there was no axial H, which is why it's very important to draw the chairs, do the ring flip, and make sure you have an axial H to your axial Br. So looking at the product, you can eliminate anything where the methyls aren't cis to each other, which is literally all of them. You can eliminate all of them except the right answer because these methyls aren't cis, these methyls aren't cis, these methyls aren't cis, these aren't cis. The only one that gives you the same answer is A, because like I said, as long as they're all cis, it doesn't matter if they're all on wedges or on dashes. So the answer is A. You did still have to do it though, because had the double bond, do the ring flip though, because had the double bond been on the more substituted side, there would not have been stereochemistry. So you wouldn't have known if all the methyls were cis, etc. Just make sure when you do these, you draw the ring flip when necessary. And I can guarantee you he's probably going to put this exact question on there because I've seen it on finals and midterms already. Okay, moving along. Number 12 asks, which statement is true regarding nucleophilic substitutions that result in the formation of a stereogenic center? So that just basically means a chiral center. Those are synonyms. So let's move down the list. All nucleophilic substitution reactions result in the formation of some inverted product. This is true because in SN2 reactions, you have all inverted product, and in SN1 reactions, you have half inverted, half not. So let's move along just to make sure, but so far A is looking pretty good. B, SN1 reactions result in small excess of a product with retained configuration. This is not true because SN1 reactions give you a racemic product, which means it's half-half. So you're not going to have an excess. It's going to be exactly 50-50. Letter C says SN2 reactions can result in the formation of a racemic product. This is completely not true because since SN2 is a one-step reaction, you're going to get the full inverted product because of the backside attack. So looking at D, SN1 reactions can result in the formation of a large excess of inverted products. This is the exact same thing as B. Basically, you're not going to have any excess of one product or another. There's a fair shot of either. So you're going to have a racemic mixture of inverted and ones with the same configuration. So the answer to number 12 is going to be A. So for number 13, I'm actually not completely sure why A is false because I know polarity does affect a reaction. I'm only giving you this question so you at least look at the answer and maybe memorize it because I've seen it on a couple different exams, so I think it's worth including. But I'm going to check in with a couple people and give you guys the correct reasoning in the group chat. But looking at a couple of the other choices, you know C is going to be true because polar A product solvent's job is to solvate cations more effectively than anything else. The other ones, like I said, not completely sure about. So I'll come back to that with you guys. Just know that the answer to 13 is A. If nobody knows why that is the answer, if I can't figure it out, just memorize this one because I've seen it a couple times. Okay, moving on to multiple choice 14. Which of the following are electrophiles? This one's relatively simple. It's exam 1 material. Basically, an electrophile is anything that wants electrons, not anything that has a negative charge. So that eliminates 1, 3, and 4 because these are nucleophiles, not electrophiles. They have electrons, so they don't want any more. So you can eliminate 1, you can eliminate A, you can eliminate C, you can eliminate D, and honestly even E, but that just makes the question really, really easy for you guys, but I'll go through the rest anyway. So BF3 is a Lewis acid, which means it accepts electrons, so that's a good thing. That means it's an electrophile. 5 is relatively neutral. It's not dying to give away or accept electrons in this case, so I wouldn't call it an electrophile. 6 is a carbocation, and we all know that carbocations are very, very unstable, and they definitely want to get rid of that positive charge. How so? They want to take in extra electrons. So 6 and 2 are your electrophiles, and that means B is your answer. So these types of questions are definitely going to be very popular on the exam. This one is from 2017, so I would definitely expect even maybe this exact question on your exam coming up. So let's go through it. You're going to hear my dogs fighting in the background because now they have found a toy. So let's go through it. We're going to do each of the reactions in order and see which one of them gives the correct major product shown. Okay. So H2SO4 over H2O. What this does is it is a Markovnikov addition of OH with the possibility of rearrangements. I would write these down on your own, make a list. When I made my chart, this is what I did. I would say what they were, what they did, and like if rearrangements were possible, if inversion was possible, things like that. But what Markovnikov addition basically means, for those of you who haven't watched my old YouTube videos or just forgot, is that it's going to add to the more substituted side. So let's go ahead and draw the intermediates. So you start with your double bond, then you're going to have your more substituted side carbocation intermediate. Oops, this is kind of ugly. So your intermediate is going to be like this. And then you're going to have a shift of a hydrogen. So your next step is going to look like this. And then your OH is going to add to the carbocation. This will be your major product for that one. Now if we scroll up, we see that is not the major product that they gave us. The major product that they gave us constituted doing a methyl shift, but you only do a methyl shift if there are no hydrogens to shift. And in this case there were. So A is not, A is not the answer. So now we can move on to B. Okay. So the reagents in B are, okay, I did that right. So the reagents in B are going to give you the Markovnikov product with no rearrangement because there's no carbocation. Instead, there's a ring formed with Hg, and he has the mechanism in his alkenes notes. It's called oxymercuration. So I would write that down in your notes, just the reagent, HgOAC2, Markovnikov OH addition with no rearrangement. So with that already, you should be able to find guess what the product is going to look like. But I'll give you the intermediates in case. Actually, there are no intermediates in this one because the intermediate is a ring. So you would either get the OH being added here or on the bottom side of the double bond, which is the exact same thing because the molecule is symmetrical. And that is not what you have as an answer choice because in the answer choice it showed that there was a rearrangement, but oxymercuration has no rearrangements possible. So B is again not the answer. Okie dokie. Moving on to C. So BH3 over OH, H2O2, and H2O is the anti-Markovnikov product with no rearrangements. So BH3, OH, H2O, and H2O2 is the anti-Markovnikov addition of OH. So what that means is you're going to have the less substituted OH in your product without any rearrangements. Okay? So looking at our starting material, that's it, okay? The double bond is here, and if you didn't know that it was an anti-Markovnikov addition, you would be tempted to add the OH to this side, but because this is an anti, you're going to add it to the least substituted side. So your product is going to look like this. And that is actually the product that they have there. So C is going to be your answer. But we can go through the rest of the other ones and see why those would not be the answer. Okay. Okay, so this one with H2SO4 over H2O. Like I said before, H2SO4 over H2O is going to be the Markovnikov addition of OH with the possibility for rearrangement. So as your intermediate, you're going to get this. It doesn't matter which side the carbocation is on because in this case they're equivalent, but you always want your carbocation to be on the more substituted side. and that is going to incite a hydride shift. So your new carbocation intermediate is going to be, let me draw this correctly. Here. And then your OH is going to add to your carbocation, and this would be your product in this case. However, that's not the product that they give you. The product that they give you is if it was a addition with no rearrangements possible. So D is definitely not the answer. And E, going back to BH3, BH3 is the anti-Markovnikov addition of OH with no rearrangement. In this case, the answer has a rearrangement because the methyl moved. Either way, that wouldn't be the answer because first the hydrogen is going to shift before the methyl shifts. So without even knowing what BH3 does, you know that this would not be the answer. Because, like I said, methyl will not shift before the hydrogen will. So E is not the answer. Although this question or these series of questions are technically open-ended, these are questions that I feel could very easily be transitioned to multiple choice. So I would make sure that you're able to do these so that you can do well on the exam. So in the spaces below, write the missing reagent and or product. And well, in this case, most of them are asking for the product. It's wherever you see the blanks, the box. In case of a chiral product, show only one enantiomer. So let's start with A. So in this case, you're going to get the replacement of the OH with the BR, but as we remember from the lecture, using HBr has the, what would you call it? The risk of carbocation rearrangements, okay? So let's go through the mechanism for part A. Part A is actually a type of SN1 reaction, but because they didn't give you like the solvent, I wouldn't refer to it as that. I would just make sure you know that OH is going to get replaced by Br, and there's a chance for carbocation intermediates. So, A, I'm going to write SN1 reaction, and let's go. So you have your OH, your O is going to, or the lone pairs on your O, one pair is going to pull the H off of the HBr, and that's going to create your Br anion. And now you have water, which, as we all remember, is a good leaving group. So it's going to pop off in the second step. Okay, so now we're going to have water leaving and the generation of your carbocation. In this case, we have the opportunity for a hydride shift to occur because we have a hydrogen here that would give you a more stable carbocation if it moved over. So that is going to be the next step. The hydrogen is going to move, and your new carbocation is now going to be tertiary, which is more highly substituted. In your next step, you're going to have your addition of the Br anion. And the Br anion is going to attack the carbocation because it is a nucleophile. Okay. So your final product is going to look like this. And that's the answer to A. So moving along to the next part of the open-ended, you have a terminal OH and POCl3. So what POCl3 does is it's going to make a double bond out of an OH. It's going to eliminate the OH, leaving a double bond behind. So with that, you can answer the question right away. But either way, I'm going to give you the mech that I have for POCl3. Okay, using our starting reagents. So the first step is that the electrons from the O are going to attack the P, and these are going to move the electrons in the ketone up. So you have OH plus bonded to the P. With all the CLs still there. And then the next step is that pyridine is going to come and deprotonate the OH. So pyridine, because I didn't draw this in the box, but POCl3 is always over pyridine. Sometimes he doesn't include it because it's implied. So it's going to pull off the H. These electrons are going to go back into the O, and that is going to give you, I hope I didn't, okay, P, Cl, 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 okay, so I'm going to zoom out, and then I'm going to erase. So the next step is that the electrons from the ketone, or like what was a ketone, the electrons from the O in the POCl3 are going to come back and rejoin, and this is going to kick one of the CLs off. That makes POCl3 a good leaving group. So for the next step, you're going to have pyridine again. That's not good. Come, and it's going to pull off a H that is adjacent to the giant group. So I'll show you what I mean in a second. So it's going to pull off, not that one, this H, and this is going to cause the elimination to occur, because when it pulls off that H, the electrons from the H are going to go into the molecule, creating a double bond, and because this carbon will now be overloaded, it's going to kick out the ginormous PCl2O2 group. And that is going to give you your product, which is just this. Okay, so I'm going to move that back into the box. So that is the answer to C. Moving on to D, the mechanism for SOCl2, I'm actually going to draw again on another page, but that's okay. Let me find it. I apologize. Okay. So. So all SOCl2 is that it's going, all SOCl2 does is that it's going to replace the OH with a Cl, but in doing so, it's going to cause an inversion of chemistry. So the reason why people like to use SOCl2 is because you can't have a carbocation rearrangement when you use it. So say you used HCl instead, you would have a carbocation rearrangement, but SOCl2, you're going to have inversion with no carbocation rearrangement. So let's get into the mech. Okay. So your electrons from your OH are going to come and attack your SOCl2, and this is going to form a giant complex that we are very used to seeing now. Okay. So that is our first step. Oh, wait, it also kicks off a Cl. Might be. So I'm going to go ahead and erase one. So that's the first step of the SOCl2 mechanism. And the next step, you're going to have pyridine. Oops. Pyridine is going to come in and remove the H on the O. So deprotonate it. I forgot my double bonds in pyridine. Okay. And that is going to give you this product. Alrighty. And I'm going to erase to add the next portion. Okay. And you also had the protonated or the protonated pyridine as a counter ion from before. But let's move along. So the Cl that you kicked off in the earlier step is actually going to come in and attack this whole group, or really the carbon attached to this whole group, and that is going to give you the Cl addition on a wedge. So your Cl anion is going to come and attack this. Oops, I didn't do it in red. Going to come and attack this carbon because now this is a good leaving group, so it's going to leave. And as your product, you're going to get this plus the SO2 plus Cl minus. Okay. Oh, reason why the Cl minus, before I forget, because when this comes and joins the O, one of these get kicked off. Might be. Alrighty. So your answer to D is just going to be this. And we're going to do that mechanism again in case it was confusing, because it's also going to be another question at the end of the exam. So that's it for D. E is going to be a series of reactions, and E is a little bit harder because you have to think about how you could get that product. So if you start with an OH and you end with an N3, N3 in general, when you're using azide, it's characteristic of an SN2 reaction, which makes sense because you're going to have an inversion of stereochemistry. So my logic is, okay, if I know I'm going to have an SN2 and I have one inversion of stereochemistry, that means my first step is going to probably just be making it a good leaving group without changing the stereochem. Okay, so let's go through how to do that. Okay, so the way that you make a good leaving group from an OH without changing the stereochem is by using tazolate or tazoyl chloride. This, I believe, is in the alkenes chapter or the alcohols chapter. So the reagents for tazoyl chloride are TOSCl over pyridine. And the mechanism for this one I wouldn't memorize because I don't think it's going to be important. I would just memorize the reagents and what the reaction actually does. So that's going to replace the OH with O-tazolate or OTS. And it's going to keep the same stereochemistry, so it's going to stay on a wedge. And now you want to do an SN2 reaction, which we're all very familiar with the one-step mech. I don't feel like we need to go through it again. So you're going to use NaN3 because you want to make sure that your N3 is balanced, your negatively charged N3. And you could use any polar aprotic solvent. In this case, I'm just going to use DMSO, and that will give you this answer. Okay, so last but not least, we're going to do the mechanism for SOCl2 over pyridine. All right, which we already did, but you know, it's good to repeat. This is one of the more important mechanisms, so it's worth remembering. And I'm going to be doing this one with full detail, all of the lone pairs, just so you know exactly what he's expecting for the exam. Okay, so as usual, the electrons from the O are going to come and bond to the S. This is going to kick off a Cl. So that is going to give you this. Plus the Cl anion with all 4 of its lone pairs. In the next step, which I don't actually have space for, so I'm gonna go over this with white because I've been writing too big. Okay. So in the next step, you're going to use the pyridine to deprotonate. Oops. Oh, no. I actually forgot to write in the plus sign. But in the next step, you're going to use the pyridine to deprotonate the O. So pyridine is going to deprotonate the O. And the electrons are going to move back to the O. Okay. So in the last step, you're going to have the Cl coming back and attacking your carbon with the good leaving group on it. I'm going to do it down here just for space reasons. But obviously in the real exam you would do it, well, you guys are doing multiple choice, but normally you would do it on the line. You don't have to be super anal about drawing the, well, it doesn't matter, you guys are doing multiple choice. Never mind. Okay, so that's going to come and attack it. And that is going to give you your product, oops, of Cl on a wedge because it attacked from the top, SO2, and Cl anion. And that is the answer to the mech. And you finished the pre-mock. Congrats. Feel free to ask any questions in the group chat. Like, you can message me privately. A lot of people have been sending me old exam questions on private, although I wish you guys would do it in the public group chat. Like, I get maybe you don't want everyone to see what questions you're asking, but like, who knows, you might help out somebody else. Either way, feel free to message me whether you want to do it in the group chat or on private of any of the old exams. Please check them out. They're under Sakai, under the O'Connor course. You have to click his folder first. I know it does say like old exams earlier than that, but go on O'Connor's folder, then hit old exams. And it should be under practice exams and practice exams answers. Okay, and I'll make